Welcome to 8.4 Trigonometric Substitution. This is the first day on this topic. So why would we use trig substitution instead of all the other methods? All right, well, first, trig substitution can help with integrals that have square roots. So we're going to look at what we're going to use when we're going to use it. And then we can use some Pythagorean trig identities. So set up some triangles and go from there. So just kind of a review, all right? Make sure you get these down, these three integrals dealing with inverse sine, inverse tangent, and inverse secant, all right, to deal with those integrals. So trig substitution, let's just kind of zoom in on this box here. All right, so as we are going through this, all right, when would we use trig substitution? Well, one key is u is going to be the variable and a is that constant value, okay? So whenever we see an integral that has the square root of a squared minus u squared, that's where we want to let u be a sine of theta, okay? So keep in mind we'll be in quadrants 1 and 4, okay? And then we'll be able to use cosine. So we'll be able to use a trig substitution there, okay? And then we'll set up our triangles and go from there. That will help us when we're substituting everything back. When we see an integral that has the square root of a squared plus u squared, we want to let u be a times the tangent of theta, okay? And just remember, you know, we're again in quadrants 1 and 4. Then finally, if we come up with, or we see an integral that has the square root of u squared minus a squared, so kind of the reverse of that first one, we're going to let u be a times the secant of theta. And we'll set up our triangles all accordingly, okay? So that's just kind of our notes. These are our three trig substitutions that we're going to use. Again, familiarize yourself, remind yourself of these integrals over on the right-hand side. Okay, let's dive right into our first example here. All right, so we're going to integrate dx over the square root of 4 plus x squared. Okay, so what are we looking at? Well, hopefully we recognize this goes along with example 2 up here. Okay, so if that's the case, I see the square root of a squared plus u squared. So a squared plus u squared. All right, so we're going to do a little side note here as we dive through this. So I know I'm going to be using tangent, okay? So we have the square root of a squared plus u squared. A is going to be 2, u is going to be x. So we're going to let u be a times the tangent of theta. So that means x equals 2 times the tangent of theta. All right? So what is x squared? Because x squared is where we're going to make our substitution. X squared is going to be 4 tangent squared of theta. All right, now integrating, right? Or sorry, taking the derivative, then we get dx equals the derivative of tangent is secant squared. So 2 secant squared theta d theta, and we're going to make that substitution, okay? Also, let's draw that triangle. So remember from up above, we're dealing with this middle triangle right here. So theta is our angle, across from theta is our u, next to theta is our a, and then our hypotenuse is the square root of a squared plus u squared. Okay, so now let's dive back and let's make our substitutions. Okay, so instead of dx, we have 2 secant squared theta d theta. Then it's the square root of our a squared, so 4 plus our u squared is 4 tangent squared theta. Okay, so what we did now is we can factor out a 4. Now we're just a matter of cleaning up this integral. Okay, so if we factor out a 4 here, all right, we're left with 1 plus tangent squared of theta underneath that radical. Taking the square root of 4 is where we get 2 from. Using a trig identity, 1 plus tangent squared is simply secant squared. We can now cancel out these 2's. Those cancel. Taking the square root of secant squared, we're just left with secant in the denominator. So now we have secant squared over secant, which gives us the integral of secant theta d theta. Now remind yourself, what is the integral of the secant of theta? Well, this is the natural log of the absolute value of secant theta plus tangent theta plus c. So now we need to substitute back in because we don't want our answer in terms of theta, we need our answer in terms of x. So we're going to go back up to our triangle that we created over here, okay? So what is the secant of theta? Well, the secant of theta is the hypotenuse over adjacent, all right? So the square root of 4 plus x squared over 2. The tangent of theta, opposite over adjacent, x over 2. And now we're back in terms of x. Okay, now we're just kind of cleaning things up. So as we clean things up and use some log properties, all right, since we're both dividing by 2, we could combine those. And then remember the log properties, if we're dividing, we would subtract those log quantities. Okay, so we get the natural log of the absolute value of square root of 4 plus x squared plus x minus ln of 2 plus c. So this whole thing is still a constant, so we can just lump it all into the same plus c scenario, and we get our final answer here. Moving on to our second and final example. This one's a little bit more hefty, but that's okay. So we want to integrate. Now we've got this definite integral from 1/2 to 1 of 1 minus x squared to the 3/2 over x to the 6th. The first thing I'm going to do is simply rewrite that numerator. So this is really saying the square root of 1 minus x squared cubed over x to the 6th. So now I'm looking at the fact that we have the square root of a squared minus x squared. So this is a scenario where we're going to let a be 1 and u be x, and we're going to let x equal a times the sine of theta, so a is 1. Taking the derivative, dx is cosine of theta d theta. Right away I'm going to draw my triangle because we'll need that when we make our substitutions back. Okay, so now we're going to substitute everything in, okay? So a is 1, x squared, I'm simply squaring that. We just get sine squared theta. We're cubing that square root. Over, instead of x squared, we know what x is, so it's sine to the 6th theta. Remember, dx is cosine theta d theta, so that's where this piece comes from. Don't forget, since it's a definite integral and we made a substitution, we're now changing those limits of integration to a to b. Okay, we now know what 1 minus sine squared is. We can make that trig identity as cosine squared and substitute that. Okay, and then we're just carrying everything out with us. The square root of cosine squared is cosine, but then we're cubing it, so that's going to give us cosine cubed times cosine is where we get cosine to the 4th of theta over sine to the 6th of theta. Okay, so now we're going to jump to our little side note. Cosine over sine, right? Cosine to the 4th over sine to the 6th is really, we can break it up. Cosine to the 4th over sine to the 4th times 1 over sine squared. So that's the same thing as this right here, okay? But now we can rewrite it. Cosine over sine is cotangent to the 4th. 1 over sine squared is cosecant squared. So why do we want to do that? Well, now we can substitute that back in and see where that gets us. Okay, So now we can do a U substitution. All right. So U substitution, remember back a few videos. If we let U be cotangent of theta, then du is negative cosecant squared. So that takes care of this piece right here. Okay? Now we're going to integrate. So since it's negative cosecant squared, we're going to pull that negative out. Notice I changed my limits of integration one more time because now we're in terms of u and not theta and not x. So now we're integrating u to the fourth, which we can. No big deal, all right? But now we're going to have to do a few substitutions in reverse. So when we integrate u to the fourth, well, negative u to the fourth, we get negative u to the fifth over 5. Now we're integrating from c to d, but let's make our substitution back in terms of theta. So what's u? Well, u is cotangent, so we really have negative cotangent to the fifth of theta over 5. Our limits of integration are now back to a to b, okay? Now, what's another way we could rewrite cotangent? Well, that's like saying cosine over sine to the fifth power, still a to b. Now we're going to use our triangle to get back in terms of x, okay? So remember, our triangle is way up here. So if we go back and use our triangle, what's the cosine of theta? Well, the cosine of theta is the square root of 1 minus x squared over 1. Or simply the square root of 1 minus x squared. The sine of theta, opposite over hypotenuse, so it's just x. Now we can change back our limits of integration. Now we're back to in terms of x, so we're 1/2 to 1. All right? And so now we can integrate through, or we can evaluate through, all right? And when we do, ultimately, we'll get our final answer of 9√3 over 5, okay? And you might wonder, well, how did I go from the square root of 3 cubed, or to the fifth power, to just 9 times the square root of 3 all over 5? Well, kind of looking at it this way, the square root of 3 to the fifth is the square root of 3 squared times 3 squared times 3. Square root of 3 squared is 3. Square root of 3 squared is 3, so 3 times 3 is 9, and we're left with that root 3 underneath. So take a look at this. There are lots of steps to it, all right? A few substitutions that we needed to do. The first one was that trig substitution, and then a u substitution to get us back through. If you have questions, make sure you let me know.